The first answer depends on which layer are you talking about. If you recall the 5-layer reference protocol with a thin waist in modularization principle behind the internet design, there's the application layer, there's the transport layer, there is the network layer, there is the link layer, and then there is the physical layer. The speed at different layers are different, and it involves different amount of overhead and control signals. So when you are quoted a speed number, you should ask, are you talking about the physical layer or the link layer, or which layer are you talking about? Eventually, what I as a consumer care most about is the application layer speed. But then this is a lot more tricky to measure and quote. And sometimes each layer is actually decomposed into many sub-layers. For example, in Wi-Fi, they are responsible for designing these 2 layers and standardize them. In cellular network, they often is responsible for standardizing these layers. And in LTE, for example, the 4G cellular, they break the link layer, layer 2, further into 3 sub-layers. One is called MAC, it's medium access control, which controls the multiplexing of data in different logical channels and then decide the scheduling of packets. Then the second one is called RLC layer, radio link control layer, which controls segmentation, reassembly of packets, also local retransmission of lost packet. Then there's yet another sublayer called a PDCP, is a packet data convergence protocol layer. It processes header compression, security in layer 2, and also handover. So each of these introduces overheads, and the speed therefore differs. Now the second answer depends on where are you talking about the measurement of speed. This is a simplified picture of, say, the LTE network. Let's say we add your radio link with this zigzag, and that is your wonderful smartphone. And let's say also add a smaller cloud, that's the Google data center with the YouTube server with your favorite YouTube video bits stored in there. So when we measure speed, we have to start with a point and end with a point. Okay, the source and destination of the speed measurement. Let's say the source is here. Okay, that's obvious. Now, where's the other end point of your speed measurement? It could be here. Okay. Now, in LTE, they do not call this base station. Don't ask me why. They give it a new name called evolvable node B. In 3G, it's called node B. In 4G now, it's called eNode B. Okay. But essentially, it's the base station. Okay. But the base station doesn't have your YouTube video. Right. So you can measure this, and this is often the number that you are quoted with in commercials of 3G and 4G. Okay. It's the physical layer, air interface only speed. But then beyond this point, there's another big chunk of the end-to-end connection, which is often called the cellular core network. The phrase core network can refer to different things, such as core optical network, core ISP network. Here we refer it to whatever lies behind the air interface provided by a single entity, such as your wireless ISP, okay, like AT&T Mobility or Verizon Wireless, if you're in the US. And this is managed and built by a single entity. Okay, it consists of many boxes and many software. In advanced material part, we'll talk much more about why do they exist and what do they do exactly. At this point, suffices to say that they do exist. And they add overhead, they add propagation delay, queuing delay, processing delay, and among them include things like the S gateway, the PDN gateway, as well as other servers with software such as PCRF, which controls scheduling, billing, charging, such as the HSS database and the MME software, whatever they mean at this point, in charge of the mobility support, without which you wouldn't have a mobile network. Okay, so dotted line represents some kind of software interaction, and the straight line represents an actual wire physically connecting boxes. In fact, there are a couple of more boxes. So that's the second part of the end-to-end, the core network. In LTE 4G, it's called Evolvable Packet Core, EPC. Okay. So packet switched based kind of core as opposed to circuit switched core in earlier generation of cellular network. And they just love adding the word evolvable. And then is the public IP network, okay, which is actually huge, and it can traverse multiple ISPs and many different routers and switches and links, and fiber and so on. Then it eventually goes into the Google data center with a particular YouTube sitting in there. So there are A, B, C, D, at least 4 big chunks of the end-to-end connection, okay, with 10, 15, 20 links. And any one can be the weakest link that derails your end-to-end application layer speed. The third answer is, when is the speed measured? Okay, if it's in the middle of the night with very little other active users, that's a different story than at 8 p.m. And that determines the kind of non-ideal network condition you're going to encounter. For example, interference, congestion, and collision. It's actually a good time to take stock and take a look at what we have gone through in the past few lectures. Now, interference, as we saw actually back in lecture 1, is mathematically represented by something like this. X over y must be greater than or equal to some number, say 1 unit. Okay. This x is basically a linear function of the transmit power. Y is another linear function of transmit powers. And this ratio is the kind of thing that we want to handle in interference. In congestion, it is, rather than a multiplicative behavior, it is additive behavior. Okay, so x plus y must be less than or equal to some capacity, say 1 unit again. Okay. That we saw back in lecture 14, congestion control, as the constraint of the optimization. And then collision, as we saw in last lecture 18, is a binary behavior, basically. Between x and y, only 1 can be 1. Okay, x and y both can choose between transmit 1 or no transmit 0. Okay. And maybe if they both choose 1, then they'll collide. Okay, so you need x plus 1 less than or equal to 1, x plus y less than or equal to 1, but still both x and y can only be binary. So it's a binary behavior. Whether it's multiplicative constraint, additive constraint, or a binary combinatorial kind of constraint, we face interference, congestion, collision to different degree depending on the time of the day. And finally, the answer depends on what application are we talking about. Okay. Is this Twitter, or is this Dropbox? Okay. Is this web browsing, or is this downloading something from the email server, whoever provides your email? Different protocols are clearly involved in different applications. They involve different control channels across each layer. And user expectations are also different. Eventually, the speed is something that you psychologically have to anticipate. Okay. Sometimes you're spoiled, sometimes you're disappointed, and therefore the kind of expectation that you want and you need, let's say online gaming, also matters a lot to the perception of whether this is a fast or slow connection. So eventually it's the end user experience that matters. Now, when you are again quoted at your local wireless cellular network provider store, say, come, please take a look. We got 300 megabit per second LTE on service now. Okay, now you know the right answer, right question to ask, and that is, just hold on a second. Can you please tell me which layer, where, when, and for what application are we talking about the speed of 300 megabit per second? Is it the physical layer air interface in the middle of the night? Or are you talking about online gaming at the peak hour in the middle of Manhattan in the application layer, end-to-end between the other gamer and me? Well, the answer can be vastly different. But then again, if you ask questions like that, you might not be well received at the store by the sales. All right, so now we're going to go through two sets of examples. Okay, one is an air interface example, and then in the module following that is a backhaul example on TCP, and more in the advanced material.